Engineering and the Institutions Innovation Council of Dayananda Sagar College of Engineering. So on behalf of our respected principal, respected head of the department, on behalf of all our faculty members and the student friends, a very good morning to Mr. Sri Raj SV, who is going to present the today's webinar. A brief introduction about Mr. Sri Raj SV. So Mr. Sri Raj SV, currently Director for Technical and Operations, MCOG Solutions, Chennai. The MCOG Solutions is to develop unique educational and technology products in line with the curriculum and provide live product development training services to engineering students, graduates, and faculties in the field of power electronics, analog electronics, control systems, embedded systems, and renewable energy. Mr. Sri Raj is also an ISO auditor since July 2019 to provide external audit support for ISO standards such as ISO 9001 2015 and ISO 21001 2018. Since June 2014 to November 2018, Mr. Sri Raj was also an assistant professor and solar energy consultant at Sri Venkateswara College of Engineering, which is one of the renowned engineering colleges of Tamil Nadu. During 2008 to August 2020, Mr. Sri Raj worked as a design engineer at Honeywell Automation India Limited to provide control system solutions for Honeywell building management systems. So Sri Raj completed his Master of Engineering in Power Electronics and Drives and is a university rank holder at Anna University, Chennai. And Mr. Sri Raj completed his graduates during 2004 to 2018 with the Bachelor of Engineering in the specialization of Electronics and Instrumentation Engineering. He has developed a novel learning pedagogy which satisfies all the 6 layers of revised Bloom's taxonomy in the field of electrical electronics and renewable energy. He trained almost 1,500 learners through offline and online modes to develop their technical skill and passion towards engineering and understand the beauty of engineering which lies within the curriculum. Mr. Sri Raj also provided solar energy technical consultancy support and regular training services to Chennai Metropolitan Water Supply and Sewage Board. Mr. Sri Raj also conducted ISO audits for more than 45 clients, around 360 manners audited till date for ISO 9001 2015 and ISO 21001 2018. Mr. Sri Raj and his consultancy and his concern signed more than 6 engineering institutions across Tamil Nadu and Pondicherry acknowledgement of quality product and training services offered. Mr. Sri Raj published an article titled Solar Plant in Education Sector in a renowned magazine, Electrical India. He received appreciation from project manager and the crew for delivering quality hardware engineering solution for United States Naval Academy in the year 2009. He is also a 6 Sigma Green Belt holder, certified engineer by Honeywell Automation India Limited. He is also an ISO certified engineer. He also certified in solar PV plant system designed by Global Sustainable Energy Solutions, a franchise unit of GSES Australia. He also a MSME certified in e-vehicle system development engineer. Mr. Sri Raj also provided solar energy installation and commissioning consultants for residential rooftop plants up to 10 kilowatt. So today, once again, I welcome Mr. Sri Raj to present our today's webinar for the benefit of all our students. Once again, on behalf of the Department of Electrical and Electronics Engineering, the Institutions Innovation Council of Dayananda Sagar College of Engineering. A very good morning, sir. I please hand over the session to you.
Thank you, sir. Thank you, sir. Very good morning, all. So first of all, thank you to the institution and Dr. Shivakumar, sir, for arranging this webinar. So let me initiate this webinar because we don't want to waste your time as well. So we'll quickly move into the content. Okay. So for to have a good internet connectivity, so what I'm doing is I'm going to switch off the camera for a while. Okay, and then once the session is finished, we can have some interaction if it is needed by switching on the cameras. Right. So let me switch off the camera and start my presentation.
Please load your presentation, sir.
Yes, yes. Okay. I hope you can see the screen now. Yes, sir. Are you able to see the screen?
Just a moment, sir. There is some.
So if you're able to see the screen, the participants, you can type in the chat box. You can type this in the chat box. You can see a circuit and a board and transformer steps. If you are able to see, please type this in the chat box. Very good.
Yes, sir.
So thanks a lot. See, this is not going to be a complicated session, or this is not going to be a session which puts your head so tight to understand things. This is not going to be like that. This is a very simple session, okay? And you are going to understand some concepts which you have learned already, but I put in the right format, okay? The format which you can learn so easily, okay? And then I also tell you that how to use those concepts to develop products. Because as I said, MCOG solutions, sir said about MCOG solutions, what we do actually is we are developing some products which can be used by the students to understand concepts and develop products within curriculum. So normally what we do after first year or maybe during first year, we'll go out of the syllabus and take Arduino board and do a lot of things. That is good, but you can understand a lot of beauty inside the curriculum. You can make a lot of products which you are from which you are actually learning through your curriculum. So we are missing out everything in the curriculum, and we are actually going out of the curriculum and taking the plug and play boards, and we are doing design. That is good at some level, but as a point of learning, we need to learn the beautiful concepts inside the curriculum, and we can develop a lot of things. So believe me that you will be able to develop, if you give me like 1 week, you'll be able to develop a new product. You can develop a commercial product. This is possible. This is not possible, or this is possible only for the students who have finished masters or who have finished PhD. It is not so. Each and every student who has the ability or the compassion to do things, you can really develop products. That is, there is no way obstruction in the path. Okay. So believe me and understand the class. Okay. So you may not understand everything because this is going to be a short session, probably for an hour. So I'll not be able to make you to understand each and every nook and corner of the design. Okay, but still I promise that you will take away some beautiful concepts today. Right? And I wanted to tell you the presentation of how we are going to give. So I have actually converted my presentation to video format. So I'll be talking with respect to the video. Okay, when I play the video, and I'll be talking parallelly. So this presentation is unique. You cannot see this presentation anywhere in this world. Okay, if you go to Google and search, you'll not be able to see the way the concepts are told. Okay, you can just verify it after the class. Right. So the topic is design and develop a high power audio amplifier for home theaters. So basically we have our own home theaters these days, right? So why don't we design a power amplifier, audio amplifier? Now why it is called high power audio amplifier? Because you will be able to use a 100-watt speaker, up to 100-watt speaker. So we call it as a high power audio amplifier systems. Normally which comes the speaker which comes Usually for audio systems could be 2 watt, 3 watt, 5 watts, up to 15 watts are coming. Okay, and if you want to go ahead, we can also use this particular design to design up to 100 watts. Now, what is the beauty, sir? See, there are a lot of audio systems in the world. Okay, even I could see cheaper audio system in Google. What is the need for this one, sir? If you ask me, so what I'll say is this is so beautiful product. Now, why it is so beautiful? Because we have not used a single IC to develop this product. As I said, this can be utilized for 100 watts power application. In normal commercial products up to 100 watts, you could see a lot of ICs, but we have not used a single IC to develop this product. Now, why we have not used a single IC? Because, as I said, the motto of MCOC Solutions is to make the students to develop these products within the curriculum. If I teach with ICs, there is no point in, I'm coming to deliver a lecture. Okay, you can do with this IC like this. You can plug and play like this. There is no point in learning. There is no point in teaching, right? So we don't pick a single IC here. Okay, we will develop everything from discrete components. So that's the idea, or that's the beauty of this particular product. Okay. Before I start with, I just play the video that which I have installed this audio system to my home theater, and once I think I will actually share. I mean, you can hear the sound right now. I'll play the song. One second. Okay, this is the product. Okay, what you are seeing now. Okay, I hope you could hear some music. Okay, so now I'll share that how I have designed this product. Okay, and what are the concepts I have learned, and I'll share those concepts with you in a very, very simple form. Okay, can we go ahead? Yes.
Your voice is not proper.
So,
Okay, now are you able to hear now?
Yes, yes.
yes,
Okay,
sir.
fine. Let's go ahead. Fine. Okay, so right now you could see 6 glass bottles. Okay, so I'm going to fill chemical fluids within this glass bottles. So you could see the chemicals are filled in each of the bottles. Now, if I connect all the top points of the fluids in each bottle, what I can get here is a linear line. Now, why this is linear? Why this characteristics is linear? Because if you look at each bottle, the difference between 2 consecutive bottles are same, right? If you look at the difference between second bottle and the first bottle, the difference between the fluid is same as that of the difference between the fluid between third bottle and second bottle, fourth bottle and third bottle, fifth bottle and fourth bottle, sixth bottle and fifth bottle, and so on. So that means the change happens in the same rate, correct? So when I connect all the top points, what I could see is a linear characteristics. So this is what we call it as linear characteristics. So linear characteristic means if the change occurs or the difference between changes or two consecutive changes are same, then we call it as linear characteristics. Okay, so let me take another sets of bottles and I'm going to fill chemical fluid. Okay, and now if I connect all the top points, this time I'll get a non-linear characteristics. Why this is non-linear in nature? Because if you look at the difference between the second bottle and first bottle, it is small. But if you look at the difference between, let's say, fourth bottle, the fifth bottle, and fourth bottle, this is huge. So that means the difference between two consecutive bottles are not same, right? So we call this characteristics as non-linear characteristics, right? Okay, so let me take another sets of bottles and let me try to fill chemical fluids in this bottle, and you tell me what kind of characteristics it gives. You can type your answer in the chat box. What kind of characteristics this will be?
Non-linear
Basically,
character.
very good. It is going to be non-linear because the difference between two consecutive bottles are not same. Okay, fine. Now let's go into the next concept. Here in this slide, you can see a device, okay? Device characteristics. You could see the violet line is the device characteristics. Now what device it is, I'll name the device as X, okay? It could be any of the devices. I'll make it as X. Now this is the characteristics. This violet line is the characteristics. Characteristics means the behavior of this device, okay? So what is this behavior? This behavior looks like a linear behavior, right? So this device has a linear characteristics on the positive side as well as linear characteristics on the negative side. That's the reason we got 45-degree on the positive axis and 45-degree line on the negative axis. Now the question is, here in yellow color you could see a sinusoidal waveform. I'm going to apply the sinusoidal waveform to a device called X, which has linear characteristics on both sides. Okay. If so, what will be the shape of my output waveform? I'll repeat. I have a sinusoidal input waveform. I'm going to apply this waveform to a device called X, which has linear characteristics on both positive side and negative side. If so, what will be the shape of the output waveform? Okay, so we'll see what will be the shape of the waveform. So to make you to understand, you could see some kind of balls kept on the characteristics input waveforms and as well as the red color TV. So in the red color TV, you will be able to see the output waveform. Okay, fine. So let me animate it so that you will be able to understand what will be the shape of the output waveform. Right. You just see the balls are moving. Okay, I'll animate it so that you can see the balls right now are moving. Right. So how this balls moves is when for example, let me take this case. Right now, on the characteristics, it is positive. Right now, if you look at the input waveform, this is also on the positive side. Right now on the TV, the ball is also moving on the positive side. Right? Now, after some time, let's say, if the characteristics, when the waveform travels on the negative characteristics, the input is also traveling on the negative characteristics, and the output is also traveling on the negative characteristics. When they're at 0 point, okay, at 0 point, you could see both are coming. Let's wait. Both will come to 0 position. Okay, so what I understand here is when I apply a sinusoidal waveform to a linear characteristics, as it is linear in nature, okay, the shape of the input waveform and the shape of the output waveform are going to be same, because the reason is the device has a linear characteristics. Okay, so this is the reason why we always start learning the linear characteristics of any device. Can you tell me a device or element which has a linear characteristics where you send the input waveform, you will get the same shape of output waveform? Can anyone tell me?
receiver,
And yes, I'll repeat. There is you can call it as a device or an element, whatever it is. I make it as X. In that X, if you apply a sinusoidal waveform or any sort of waveform, the output is also going to be at the same shape because the characteristics is linear. Can you name any element or any device? Very good, resistor. So resistor is only one element which we call it as a linear element. Why it is linear? Why we call it as a linear element? When we give an input waveform, the output waveform shape is also same. Okay, so that is the reason whenever we study any circuit, we always starts with resistor. Okay, fine. So now I'll have another device. This time I'm going with a device called Y, which has linear characteristics on positive side. You can see the violet color 45-degree line. But on the negative side, you could see almost zero characteristics. Okay. So what happens if I apply sinusoidal waveform to this particular device called Y, which has linear characteristics on positive side and almost no characteristics on negative side? So you can see the animation, and you will be able to now understand how it works. So right now, the device is on the positive characteristics. The input is also on the positive characteristics. So you can see the output waveform is resembling as input waveform, okay, because the device characteristics is linear. But on the negative side, you could see the device does not have any characteristics, correct? The device characteristics is 0. So what happens is, when the input waveform travel on the negative side, okay, as this device does not have any characteristics, you cannot see the negative portion of input waveform to the output side. Okay, now you can see the input is sinusoidal in nature, but the output is, we get only one half of the cycle. The next half is not appearing on the output waveform. Why it is not appearing on the output waveform? Because I have sent the input waveform to a device which does not have any characteristics on the negative side. Since it doesn't work on the negative side, my input waveform or the negative waveform, negative side, this portion, negative half cycle, is not appearing at the output. Now, can you tell me any device in electronics which you have studied has almost linear characteristics? I won't say it is linear characteristics, almost linear characteristics on the positive half cycle, and ideally no characteristics on the negative side. So that when you apply a sinusoidal waveform, you will only get one half cycle of the waveform. Can anyone tell me?
diode,
Very good, diode. So why we call diode as unidirectional? Because diode has only one characteristics. It has characteristics only on the positive side. If you look at the VI characteristics, it doesn't have any characteristics on the negative side. So the negative portion of the input waveform will never appear on the output side. Okay, so that is the reason we call it as unidirectional device. Right? Fine. So I hope you understood linear characteristics, non-linear characteristics. What happens when I apply a waveform to a linear characteristics? I'll get the same shape at the output. Okay. What happens when I send a wave to a device which does not have any characteristics on either side? So that means one portion will not appear at the output. Okay. So why this is very important? Because I could see a lot of people doing, put more time to research how the device will work when you do the product engineering or maybe your project. What you need to do is you need to download the data sheet of that particular device and see the characteristics. Okay, the device will go and work only as per the characteristics which is defined by the manufacturer. Okay, so it is very important that one has to refer the data sheet and refer the characteristics, and then you attempt for your projects. Fine. Okay. So now let's go ahead. Now we come to a main portion where we have a challenge. The challenge is, just listen to me very carefully. The challenge is, one person has given us a device, okay, and the characteristics of the device looks like this. Is this linear characteristics or non-linear characteristics? Is this linear or non-linear which you are seeing on the screen?
Linear.
Look at carefully. Is this linear or non? Is it 45-degree line?
Non-linear.
This is non-linear in nature because it is curvature, right? Curve. It looks like a curve. It is not a 45-degree line, right? So if you look at the slope, you can see the slope. The slope will dy by dx will be more here, dy by dx will be less here, and there is an average dy by dx at the center. Right? Fine. So this device, okay, the device, as I said, one person has given me one device which is a non-linear device. Okay. Now what he is asking me is to do a linear amplification. Okay. The person has given me a non-linear device and he is asking me to do a linear amplification. Now what do you mean by linear amplification? Linear amplification means if the input increases, output also has to increase, right, at some constant rate. If the input reduces, the output has also reduced at the constant rate. Correct. Then only we call it as a linear, right? So the problem here is a person has given us a non-linear device and he is asking us to design a linear amplification. Now I will put it in your word. This particular device, okay, is called as transistor. Okay, transistor has a non-linear characteristics. Now what is expected as a product developer is you need to provide a linear amplification using this non-linear device. Now the question is, how should I provide linear amplification using a non-linear device is the question. And this is what we are doing for the last 50 years. So now I will tell you how to do a linear amplification using a non-linear device. Okay. So before I tell you how to do linear amplification using this non-linear device, I wanted you people to look at this curve so deeply and tell me, is there any linear portion in this non-linear curve? Look at the curve entirely and tell me, is there any linear portion or linear segment in this entire non-linear curve? Anyone? Is there any linear segment or linear portion in any of the portion or any of the segment in this entire non-linear curve?
1/3 portion of that curve is linear.
Which portion?
1/3.
1/3. Okay, let me try. So I use some experiment here. Okay, animation experiment, and let's find out, is there any linear segment in this non-linear curve? So what I'm doing is I have a 45-degree line here. I'll try to navigate this line throughout this curve, and I see, is there any linear segment in this non-linear curve? Okay, since it is 45-degree line, you just see, I'll navigate it point by point. If this red line coincides completely with the blue line, we can say that portion of that blue line is 45-degree line or linear, right? So at this point, you could see the red line is not aligning with the blue line. So we cannot say that that segment is linear portion in this curve. Over here, no, because the red line is not coinciding with the blue line. Over here, it is not so. Over here, it is not so. Over here, it is okay. It is no. This point you see almost, right? So that means this 45-degree line is actually coinciding with the blue line. So what we can, over here also you could see, right? Almost coinciding. So what we can do is we can find using this trick, we'll be able to find, there are a lot of tricks to do it. Okay, this is just a point of animation. So if you use this trick, you'll be able to understand where this linear portion available in this non-linear curve. Okay, so I'll come back. A person has given us a non-linear device, and when we see the characteristics, it is non-linear in nature, and they are asking us to do linear amplification. To do that, first I need to identify, is there any linear segment in this non-linear curve? And I did a small experiment, and I found out that this particular portion of the curve, or this particular segment, is the linear portion in this entire non-linear curve. So hereafter, for amplification, I will not be using the entire characteristics curve. I'll be using this portion, which is linear in nature, because I wanted to provide linear amplification to my customer. Okay, fine. Okay, fine. So now we will understand about another term called small signal analysis. You might have studied your electronic devices or electronic circuits, and in most of the authors used to mention something called small signal analysis. But they never say what is the meaning of small signal analysis. But in a very interesting way, I'll tell you why they call it a small signal analysis. Okay. So in this lecture, in this slide, you are going to understand what is the meaning of small signal. Okay, let's try to do that. And before that, I just want to recap that this blue color line is the non-linear curve, right? Which we have seen in the previous slide, and we did a small experiment to find out which is the linear portion in this non-linear curve. Okay, and we figure out the linear portion in this non-linear curve, and this red line is nothing but the linear segment of this non-linear curve. Now, on the origin, you could see a sinusoidal waveform. Okay, right now I'm going to move the sinusoidal waveform to the place where there is a linear segment. Okay, so right now I'm moving through animation. I'm moving my input signal to the place where there is linear segment. Now, what you could see here is this input waveform is not completely accommodating inside this linear portion, right? You can see some parts of input waveform actually it is projecting outwards or outer to the linear segment, right? So what happens when I have a big input waveform which I cannot accommodate inside the linear segment or linear portion? What I'll get? I'll get a non-linear amplification, right? So my duty is to provide a signal which accommodates or sit comfortably in the linear portion of the characteristics curve. Otherwise, what happens? I will not get a linear amplification. I'll get a non-linear amplification. So if I have a big signal, I will not be able to accommodate it in the linear segment. So what I can do? I can compress the signal to small, or I can have a small signal so that this actually sits comfortably in the linear portion of the characteristics curve. Such a signal which is small and which is beautifully sitting inside the linear portion of the characteristic curve is called as small signal, and that analysis is called small signal analysis. Okay, so why it is small signal or small signal analysis is because we wanted the signal to sit comfortably in the linear portion of the characteristics curve. Okay, so I'll again tell you later that what happens if it is not sitting in the linear portion of the characteristics curve. Okay, and you might have some doubt, sir, whatever you say is good, small signal, but I have also studied about large signal analysis. Then what is large signal analysis? Okay, I'll tell you that also a little later. Okay, so I hope you understood up to this. Okay, so why we wanted the signal to sit comfortably in the linear portion? Anyone? Why I wanted the signal to be small, which sits in the linear portion comfortably? What is the benefit?
To get the output, sir.
To get what output? You will get output, but what output is expected?
Linear output.
Very good. Linear. Linear means what? If I give sinusoidal shape, the output is also the sinusoidal shape, right? So that is what we have seen as linear, right? Okay, so this is what expected as output. Okay, so that is the reason we do small signal analysis, right? So let's go ahead. Requesting Shivakumar sir, once your time is over, or when I reach the time, the required timing, you just tell me. We will wind up because the session is little long. Because I don't want to do a fast approach. So let me go slow. Whenever you want to wind up, you just tell me, sir. We'll wind up by that time.
No, sir, we can have some the flexible minutes. You just
Okay,
complete
no
it
problem.
in a fine way, no issue, sir.
Okay, sir. Okay.
Thank you, sir.
Thanks.
Please continue, sir.
Yeah, thank you. Okay, let's go ahead. Now we are going to understand another important concept. So far what we understood that one person has given a nonlinear device, and we did an experiment that we found out there is a linear portion in this nonlinear curve, right? And remember that linear portion is not at the origin, it is actually far away from the origin, right? And we also understood our signal has to be quite enough size so that it will be able to accommodate within the linear portion of the characteristic curve. Now, in the previous slide, I have moved this sinusoidal signal, which is at the origin, to the place where there is linear segment through animation, right? So how should I practically move the signal? Can anyone tell me what should I do so that I can move the signal which is sitting in the origin to the place where there is linear segment? Earlier I did through animation, I moved it through animation, but I cannot, when it is circuit design, we cannot push it physically or through any other mode, right? So electronically, what should I do in order to move the signal sitting at the origin to the place where there is a linear segment?
You take clamping.
Not clamping exactly, kind of clamping only that.
Increase the voltage current.
We need to provide some offset voltage. Okay, we need to provide some offset voltage, and we need to move it. Something like clamping. Also, you said something like clamping. We call it as offsetting. Okay, this process of shifting the waveform, which is sitting at the origin to the place where there is linear segment, is called as biasing. In your electronic circuits, you call it as biasing. Okay, so in most of the books, even local author books, I have seen that they have written that biasing is a technique to switch on the transistor. Remember, biasing is not a technique to switch on the transistor. Biasing is a technique which is needed only for the amplifiers. Why we need it only for the amplifiers? Because the linear segment is not at the origin. The linear segment is far away from the origin. So if my signal sits at the origin, I'll not be able to get the linear amplification. So I should, clamp it. As you said, I need to clamp it, or I need to move it, or I need to push it to the place where there is linear segment. And that is the reason we need to bias the transistor properly. If you are not biasing properly, the signal will not sit in the linear portion of the characteristics curve. So your output will have some kind of distortion. You might have traveled in share autos and all, right? You could hear audio songs. Along with that, you can hear some noise. It's only because of the poor biasing. And sometimes you'd also have seen that when we buy the product, initially the sound is so beautiful. After some days, it gets it gets some kind of distortion. Why? Because this biasing will get affected because of temperature also. So once the biasing is affected, the input waveform and output waveform are not going to be at the same shape, right? So there will be kind of distortion. Okay? So this is called biasing. Okay. So remember, biasing is a technique which is applied only for amplifier circuits to move the signal which sits in the origin to the place where there is linear segment. Okay. So I will tell you how to do biasing and all. I have used these techniques, everything in my circuit. Okay. Fine. So let me move ahead. So I hope you understood so far. So far we have learned what is small signal analysis, what is linear circuit, and what is biasing. Okay. So let me move to the next understanding. Okay, so we will see now biasing with respect to the circuit. I'll show you perfect biasing. I'll also show you imperfect biasing, and we will see how the waveform get changed. Okay, fine. So assume in this circuit I have biased it properly. Because I cannot tell you all the circuit, how to choose all the circuit components right now. For your kind information, note on the resistor R3. The value of resistor R3 is 4.7K, right? So just note this value, okay? Keep it in mind. So for this particular circuit, I kept this resistor R3 as 4.7K. Just assume that I have biased it properly. Over here, you can see the blue color sinusoidal signal, yellow color sinusoidal signal. Blue color is the input signal, and yellow color is the output signal. You could see the shape of the waveform. The shape of the waveform is same. There could be 180-degree shift. That is a different story. But you just look at the shape of the waveform. The shape of the waveform is same, right? The input signal and output signal. Now what I do is I'll try to change the value of R3 a little. Okay, I'll have a different. So I'll take the different circuit. Okay, in this particular circuit, if you look at here, I have kept the R3 values 1.35 kilo ohms. Okay, so assuming that this is actually not a properly biased circuit, you could see the input signal and output signal. See, the output signal has a flattening at the bottom, right? And there is a huge peak at the top. But the input signal is pure sinusoidal, but output is not perfect sinusoidal, right? So this is what we call it as improper biasing or imperfect biasing. So what this kind of signal, output signal can cause? It can cause, because flattening of signal is nothing but a DC component in the signal. Okay, when a waveform looks like a flattening, it means the waveform will have DC content. Okay, when this DC content goes to the speaker, it creates kind of humming noise. Okay, so we have to be very careful with the biasing. It's very, very important. Why? When I change the value 1.35K to 35K, it means that the input signal is not exactly sitting on the linear portion, linear segment or linear characteristics area. It is actually skipping maybe above or below. Okay, so that is the reason we are getting this imperfection, right? Now, I also told you that some time earlier, we have studied about small signal analysis, but you might have a doubt. Sir, if I bring a large signal analysis, can we do amplification using that transistor? Yes, we can do that. So I'll tell you one technique to do that. This kind of analysis I couldn't see anywhere in the most of the books, but it's a beautiful concept. Okay. Now you look at this circuit, this transistor circuit, and just note on the emitter terminal alone right now. The emitter is grounded directly, right? Emitter is grounded directly. If I ground this emitter directly, if you plot the characteristics, you could see the linear segment. You could just see the linear segment. You can see the characteristics. The linear segment, the width of the linear segment is very small. I'll plot it using dotted lines. Please wait. Let me show you the width of the linear segment or linear area. Yeah, you could see here, the width is very small, correct? So I can accumulate only very small signal here. Now what I'll do is I do some changes in the circuit. Now you could see the width will widen. Okay, so let me change the circuit. Okay, over here, how I have changed is to the emitter, I have connected a resistor. Okay, and this resistor created this wide range of or wide area of linear portion. So if I have a wide area of linear portion, what I can do is I'll be able to accommodate a large signal. Now coming back, what is this resistor? In most of the textbooks, it is written as degenerative resistor or gain reducing resistor. Why means if you place this resistor here, the overall gain of the circuit will reduce. But remember, as a designer, we are not worried about the gain because gain can be multiplied in several stages. But what as an engineer, what I will focus, I have to focus that whether I am able to capture the signal completely or not. Or I have to make sure whether my signal is completely in the linear portion of the characteristic curve or not. Okay, so this point is not captured in many of the books. So remember that if I reduce the gain, this is not going to affect anything in my circuit. But if I'm not capturing the input signal properly, my output will go wrong. Okay, so during the initial stages of our amplifier design, we give more concentration to capture the signal completely. That means we need to provide a sufficient linear space to the input signal to sit comfortably. Then we can improve the gain stage by stage. That is not an issue at all. Okay, so the point is adding this resistor not only reducing the gain. There is a negative impact given in most of the books, but there is a huge positive point is you can widen the linear portion of the characteristic curve. Thus, you will be able to place a large signal. Large doesn't mean that high. I mean 10 volt or something like that. Maybe 0.5 volt, let's say. Okay, normally the signal will be in millivolts range. Okay, so maybe up to 0.8 volt or 0.7 volt you will be able to accommodate properly. Okay, so there are limitations with respect to the transistor, different transistors. So right now you have to take away this one. You need to understand biasing is very important. You need to understand if the biasing goes wrong, what happens. You also need to understand how to widen, if I get a large signal, how to widen the linear segment so that I'll be able to accommodate even a large signal as well. Fine. Now let's go to the next stage. So next stage is I'll share the how I have designed this circuit. I'll show you the final demo as well. So my first stage of circuit is nothing but a differential amplifier stage. Okay. So the first stage is differential amplifier stage. Now, why I've kept a differential amplifier? Now, you need to understand how this differential amplifier has been come, or that concept has come. Normally, there is no differential amplifier earlier. Okay, we have only common collector, common base, and common emitter. But what happened? There was a problem with the common emitter. When you make the transistor inside IC, can see a lot of transistors are there in ICs, right? So when we do that IC fabrication, there were a lot of difficulty faced by engineers to accommodate common emitter circuit. Why? Because this common emitter circuit has three capacitors. You could see C in, C naught, and CB. We call bypass capacitors. Okay, but C in and C naught are small capacitors. But the capacitor, which you can see at the emitter terminal, which comes around 1000 microfarad, which is not at all practically possible to integrate it, to put it in integrated circuits. Okay, so when you make this common emitter amplifier into IC fabrication, we will not be able to do it because the reason is there are huge capacitance can't be made inside integrated circuits. So that is the reason people thought a different way that there should be a circuit which provides the same feature of common emitter but should not have any capacitors. Okay, I try to avoid the bigger value of capacitance, and that's how people got the idea of differential amplifiers. Okay, so in most of the IC configurations, you could see differential amplifiers the first stage. Even if you study your linear integrated circuit, you have an op-amp characteristics architecture. You could see differential amplifiers at the first stage, right? And you cannot see any common emitter amplifier in any integrated circuit architecture. Fine. So now let's come to understand why I have used the idea of differential amplifier in my product. So main idea is I want to reject the noise. Now I'll just do a demo and tell you how I am rejecting the noise. To make it to understand, assume that I have two copper rods. You can see two copper rods, which is embedded with wires. You can see some signal, right? Some signals are there. Assume yellow color signal, which we can call as V1 and V2. Okay, so I'll repeat. There are two copper rods, and two copper rods are embedded with signals, which is in yellow color. One signal, let's call it as V1. Second signal, we call it as V2. By looking at the screen, you can understand V1 signal looks larger than V2. Correct? So I made V1 little larger than V2. Fine. So I'll repeat. I have two copper rods embedded with signals V1 and V2. V1 seems to be larger than V2. Now what I'll do is I'll bring some guys here, okay? And these guys are your favorite guys, or nothing but some. You would have seen in most of the TVs, earlier TVs, when the signal is not there in the TV, you could see some sort of signal like this. This we call as noise signal. Okay, so I'm trying to mix the noise signal in these two copper rods, which carries signal V1 and V2. So I'm going to mix the noise equally. Okay, equal amount of noise at V1 and equal amount of noise to V2. So I'm trying to mix now. So right now, we cannot call V1 and V2 as good signals. We can call it as signals with some noise, carrying noise, right? So what I'm going to do is, I'm going to take these two noise carrying signal to a differential amplifier circuit. Okay, so what differential amplifier does? We know differential amplifier amplifies difference between two signals. Okay, it amplifies difference between two signals. So what this differential amplifier does initially is, it calls the two noise signal out. Okay, let's call the two noise signal out. Okay, one. Okay, second guy has come. And as I said, the amount of these two noise signals are same. Their difference is going to be 0, right? So what is their difference? The difference is 0. So that means now the noise signal is completely neglected or rejected. So that is what we call as common mode rejection. Common mode or common signal is nothing but noise signal. When noise signal comes to pins, it actually comes at the common, the amount of noise will be same only. For example, if you look at integrated ICs, the pins are very close to each other, right? IC pins are very close to each other. So if any noise comes, the amount of noise captured by each of the pins will be same only. So when we take the signal to the differential amplifier, as the amount of noise signal is same, their difference is going to be 0. So that is why we call it as common mode rejection ratio. So normally the differential amplifier has a very high common mode rejection ratio. That means if any common signal or noise signal comes, it rejects it, or it has the infinite power to reject. So it rejects it completely. So there is no noise signal will come out at the output of the next or input of the next stage or output of the differential amplifier. Okay. So now once the noise signal is eliminated, it calls the two signals V1 and V2, and it takes the difference V1 and V2. As I said, V1 is greater than V2, or there will be a small V1 minus V2, and it amplifies this difference, and now we'll get the output signal. Okay. So this is just an idea. This is not the way to design. Okay, this is just an idea to make you to understand what is the beauty of this differential amplifier and why people use differential amplifier as the first stage of audio system, because we wanted to eliminate noise completely. Right. Now we will go and see another beautiful concept, dual supply concept. You would have studied in most of the circuits, there will be 1 plus VCC and there will be ground. Right? In most of the circuit, 1 positive power supply and 1 ground, common ground. But in some circuits, you would have seen plus VCC minus VCC, or some people used to say plus VCC minus VEE. In CMOS, we call it as VDD and VSS. Okay, so this is TTL concept, or TTL language, we call it as VCC and minus VCC, or plus VCC and minus VEE. Now the question is, why we need to have two supply or dual supply? If you look at op-amp, we connect plus VCC minus VCC. Whether it is needed or not, we connect both the supplies. Now we need to understand why we need to have dual supply concept, where we need to connect dual supply also. Okay, it is not needed that you have to connect plus VCC and minus VCC for op amps for all the circuits. It is not needed. Wherever it is applicable, only you need to connect, and we will see where it is applicable. Okay, fine. So let me go ahead and show you the beauty of dual supply and single supply. So to make you to understand, let me first take a single supply. Okay, so you could see here plus VCC on the top, and you could see the ground at the bottom. So this is a single supply. Okay, now what happens when I design my audio system using single supply concept? Okay, assuming that the Q1 is a transistor. Okay, its base is connected to input. Input means when you want to play a song, you will provide one input, right? So that input I have right now connected to ground. That means I have not applied any input signal to amplify. Okay, now the question is, if I am not applying any input signal to amplify, what should be my output? Tell me, what is the expected output? I have not connected input signal to be amplified or to get amplified. Then what is the output voltage I expect at the speaker side? Anyone?
0.
Very good, 0. So let's see whether we are able to generate 0 at the loudspeaker end using this single supply concept or not. If you look at, it will not be 0 volts, it will be around 5 to 6 volts. Now why this is 5 to 6 volts, or why here we are getting this 5 to 6 volts? Because if the signal is coming or not, we need to bias this transistor, right? We need to keep the biasing ready. When the signal comes, it goes and sits. If the signal is not coming, anyway, we have to switch on the transistor and make it to ready for the biasing area, right? So this biasing voltage is actually appearing across the speaker, and this causes some humming noise. And that is the reason in most of the public audio amplifier, before you talk, you can see a key kind of noise on the speaker, because the reason is this system would have been some problem with the supply. Okay, so if you are designing with a single supply concept, the biasing voltage will be going and sitting across the speaker end. Now, why it is 5 to 6 volts? Because normally the biasing voltage will be the midpoint of top rail voltage and bottom rail voltage. Okay, so as a thumb rule, we will bias the transistor taking the average of the top rail voltage and bottom rail voltage. In this case, top rail voltage is 10 volt, bottom rail voltage is 0. What is its average? The average comes around 5 volt ideally. Okay, so 5 to 6 volt always comes across the speaker, and you need to put a big capacitor to block it. Okay, if I don't put a big capacitor, this voltage will cause some humming noise in the speaker. Okay, so now let's see how to stop this using dual supply concept. Okay, in this dual supply concept, I have plus VCC on the top and minus VCC on the bottom. So I'll also do the same case that to the input, I'm not connecting anything. Okay, let's check what is the output. The output, in this case, it is coming on 0.2 volt or close to 0 volt. Why? Because as I said, the thumb rule of biasing is the average of top rail voltage and bottom rail voltage. Here in this case, top rail voltage is 10 volt, bottom rail voltage is minus 10 volt. So the midpoint is going to be 0, right? So this 0 will come across the loudspeaker and it doesn't affect the loudspeaker. And that is the reason why we need to use this dual supply concept in amplifiers, okay? To avoid this humming noise when the system is under biasing, okay? Although you apply signal or not, the system has to be under biasing and it should not affect the loudspeaker, okay? So that is what this one, right? Now the second stage, let me go to the second stage now. Here, the first stage, as I said, it is a differential amplifier stage. The second stage is going to be a voltage amplification stage. Now, why we need to amplify voltage? Because our input signal, which is played from an MP3 player or MP4 player, is going to be millivolt range. But when you take a loudspeaker, we need to provide a high RMS voltage. For example, a 50-watt speaker needs at least 20 volt RMS to provide the output at the rated power. Okay, so we need to improve the voltage. Okay, so the second stage is nothing but the voltage amplification stage. I'm not going to explain this circuit right now because you will not be able to understand. But I'll ask you only one question, that why I have connected this resistor R3, which is connected at the emitter R3, which is around 100 ohms. You tell me why I have connected this resistor. I already explained this concept.
For the gain.
Not for the gain. Any other answers?
So feedback resistance, sir.
No, sir, not feedback. We have not spoken about feedback, right? So far. I told you, I have given you one demo as well. Why we need to connect a resistor to the emitter terminal? What happens if the emitter is directly grounded? Anyone? I told you, no, some maybe 15 minutes back. That's it. Now you are supposed to remember. I have shown you one curve and told you that if the emitter is directly grounded, what happens? If the emitter is grounded through the resistance, what happens? Anyone? Okay, let it be unanswered. Okay, if you get time, you just go, make it to understand. Right. So let me show you the third stage. Okay, the third stage is going to be nothing but the current amplification stage. Okay, so basically, I don't want to explain this circuit, but I want you to tell very, very important point here, that when you use or when you do a current amplification stage, okay, you need to make sure that the voltage which you have amplified using the previous stage should not affect it. Okay, for example, I told you the second stage is a voltage amplification stage. Assume in the voltage amplification stage, you have amplified, let's say, 0.5 volt to 20 volt, which is required. Now the system has 20 volt, it is ready, pakka ready. Now what you are giving is, you are giving to this current, you wanted to improve the current also, because let's take a speaker. The speaker needs power, right, to get the sound. So obviously the current has to be improved. So we need to do a current amplification stage. So as a designer, you need to think only one important thing. When you use a current amplification stage, you make sure the voltage which you have amplified in the previous stage should not affect because of this current amplification. Okay, because we already made the voltage to be the required level. So when I give this to a current amplifier, the current amplifier should not reduce or increase the current. The current amplifier should focus only to improve the current and not the voltage. Now, if so, tell me what kind of configuration should I take so that my voltage gain or voltage will not be affected, only current will be improved. Which configuration should I take so that the voltage will not get affected, only the current will be improved during this current amplification stage? Anyone? Or I'll give you one hint. This configuration should have unity voltage gain and tremendous or more current gain. What configuration we have so that which has unity voltage gain and tremendous or infinite current gain? Any answers? not common emitter. A configuration which has unity voltage gain and finite current gain. Common emitter has finite voltage gain and finite current gain. But what we need is here unity voltage gain. Why it is unity voltage gain? Because we don't want the voltage to get affected, because we have already amplified the voltage. So it should not get affected during this stage. So that is the reason I'm going to take a configuration which has unity voltage gain and tremendous current gain. Any answer from anyone? Okay, so this is called as a common collector configuration. Okay, so when you do the current amplification, you need to use common collector configuration, or in electrical they also call it as drivers. Basically drivers are nothing but common collector configurations. So you have to use a common collector configuration as the current amplification stage. Okay, so finally, to end up with, I'll show you the demo of the product. So this is how it looks like. Okay, and I'll show you stage by stage. So this is the rectifier stage, because we will give ACS input and we need to get the DC output for plus VCC and minus VCC. So that is the reason two supplies are here, plus VCC and minus VCC. And if needed, you can go with a pre-amplifier section. Okay, that means first stage of amplification to capture the signal properly. So basically that is called preamp. So once you capture this signal, then you can go for your differential amplifier stage. And then finally you can go for your current amplification stage. So this is the current amplification stage. And can anyone tell me why the resistors are really huge during the current amplification stage? I put big resistors. You can see a white. This is nothing but a resistor. Okay. So here also you can see big resistors are there, big transistors are there. But there are small transistors for voltage amplification. But if you look at the current amplification stage here, we have big transistors and stuffs. Because the system carries current, so there should be power dissipation. It should not affect the system. So we need to have a high wattage resistors, 5 watt resistor or 3 watt resistor. And also you should have big transistors, power transistors, not the voltage signal transistors. Okay, so only on the current amplification stage you have to make sure that you put the right components. Okay. So so with this, I just do a recap. What we have understood, we understood linear characteristics, non-linear characteristics. We also understood how to read the characteristics of any device. We also understood what is meant by small signal, what is meant by large signal, what is meant by biasing, what is the use of differential amplifier, why we need to go for dual supply concept. We also understood the stages of amplification. The first stage is this stage where we need to get the signal properly, then differential amplifier stage, then voltage amplification stage to improve the voltage for the loudspeaker, and then we also need to improve the current, because the current constitute one of the component as power, so it has to be delivered so that the speaker provides the proper volume, right? Okay, so I think this is all about our session. So if you have any questions, you can ask, and you can also share your feedback if anything is there. Thank you for patiently listening to the class, and I have taken 10 more minutes, I guess so.
All of you, please switch on your cams and raise the questions, whatever the doubts you are having.
We're also conducting internship programs, so if people are interested, you can contact to Shivakumar sir. You can get my contact details from sir. and you can approach through your college as well.
You can a little more detail about your internships, the areas, what are all the areas you are
Yes,
providing,
right.
and what are all the
Yeah,
procedures. You can detail it.
yeah. Right now we are providing embedded systems. So basically, as I said, we don't want people to do plug and play. So we have 4 levels of training. The first level, you will understand the basics, and you will understand some hands-on experience in the softwares to write coding, and you will make some mini projects. Okay, to that level. Then level 2, you'll understand advanced level of embedded systems, and you'll make beautiful commercial products with respect to that particular level. And third level, you can make your own PCBs for your design. For example, you can start one product, you can write coding, you can fabricate your PCB, and you can design completely as the product developer from scratch to the end troubleshooting. And final level is the application level, where you will be able to develop products in the fields which we are doing right now in analog electronics, digital electronics, and renewable energy and control systems. Okay, so this because why this is made like levels, because we wanted things to happen so systematically. The student should learn properly. See, you're not going to spend 1 year or 6 months to do all these courses. This is a very simple course which is done. For each levels will be around 15 days. That's it, which is done through online. Okay, 1 hour or 1.5 hours per day. That's it. So if you commit yourself to learn, you can really learn within 15 into 4. Let's say 60 days of time. You will be able to learn everything, and this is equivalent to if you till what you do till PhD. So it will be in that level, but your commitment, and you have to work a lot with us. Okay, so that is the point in our internship programs. Nearly we have done almost 500-600 students so far for the last 4 months, and so we are also going to start our internship programs on April 1. So I will, if interested, you can approach me. So you can get. I'll also share my email ID and contact number. So if you're interested, you can go ahead. My name is Sriraj. My contact number, call me or WhatsApp me, and my email ID is impopsolutions@gmail.com. And students, now you can note all these things. And if you also share your feedback of this particular webinar, tell me what is, because as I said, we'll not be able to teach everything, right? It's very difficult. It's a time constraint, as well as it has to be done systematically, right? So what I thought is to give you some beautiful concepts which you have studied every day. So you would have benefited. If you have any feedback, please share. We'll be happy, so happy to hear some beautiful words from you.
Is there any doubts or clarifications? So thank you very much, sir. Once again, I convey our sincere thanks on
Thank
behalf of the Department of Electrical and Electronics Engineering and the institution's Innovation Council, the respected principal, head of the department, all our faculty and staff members, the students, and on behalf of our management for spending your valuable time for an informative and interesting the webinar. Once again, we convey our sincere thanks. Thank you very much, sir.
Thank you, sir. Thank you so much, sir. Thank you. Can I log out, sir?
Yes, please.
Yeah, thank you, sir.